everyone. Let's start lecture 28, and the course is corrosion protection methods. And if we observe carefully for the last few lectures, we have been talking about effect of environmental factors and associated corrosion behavior and subsequently corrosion protection. We have talked about removal of corrosives, and then we talked on the effect of oxidants or oxidizers on the active metal as well as passive metal. And we have seen that if we add oxidants in case of active metal, corrosion rate increases. So, their removal of oxidant would be helpful. But in case of active passive metal, at times addition of oxidizer can be helpful to get better protection, because it will take the material into the stable passive range quite easily. Now, today we will talk about the effect of concentration of corrosive, and here we are not talking about oxidizers. Here we are talking about only the corrosive. For example, HCl is a corrosive, then we can talk about HNO3 as a corrosive. There, what happens if we increase the concentration? Now, we will also talk about effect of temperature. At times, temperature increment can actually reduce corrosion rate. Now, that is very specific to certain cases. That is very specific, and we will have some examples. But most of the cases, almost all the cases, increase in temperature actually increases the corrosion rate. So, if we have a low temperature, corrosion protection is better. So, we will talk about and discuss those cases with a lot of examples. So, at the same time we will also talk about effect of velocity, because in many of those practical applications, the solution or the electrolyte is not stagnant, rather those are flowing electrolytes, and those cases situation could be different. It's not like what happens in stagnant condition. Sometimes increase in velocity helps in reducing the corrosion rate. For example, crevice as well as pitting corrosion, that can be reduced if we maintain certain velocity. But in certain cases we can actually increase the corrosion rate if we increase the velocity. So, those instances also we'll try to look at. Now, when we talk about velocity, we would have to also look at the mechanism. If the mechanism for corrosion is guided by the concentration polarization, the situation could be something, but if it is guided by the activation polarization, then situation could be something. And apart from that, of course, the velocity or the abrasion part would come in, where erosion becomes important. So, we will talk about those things in our following discussion. So, let us look at the effect of change in concentration of corrosive, or rather increase in concentration of corrosive. So, we will have some examples. Generally, the curve pattern could be of this nature. If we try to find out the corrosion rate, this is the concentration it is increasing this way. In certain metals, the pattern looks like this, and then once certain critical value is achieved, the concentration value, then the corrosion rate increases at times exponentially. Okay. So, this is one sort of behavior. So, we can see that there are two segments. One is this one, segment 1, and there is another segment starting from this. So, this is segment 2. Now, this kind of behavior we can notice, let us say in case of segment 1, where we can see nickel in NaOH or 18.8 stainless steel in HNO3. Now, in this case, this nickel, if we dip nickel in NaOH or dip 18.8 stainless steel in HNO3, immediately those alloys or metals will get to the spontaneous passive zone. Okay, so there's a passive zone will be achieved very quickly, and then definitely it will maintain that passive zone. It will that material will be maintained in the passive zone for a wide range of concentration. And this particular thing is also related to the mixed potential theory. In brief, if we try to look at the mixed potential theory, and this happens in case of active passive metal. So, this is potential voltage and then log I ampere per centimeter square. Now, if I try to look at the active passive metal, so it will have a curve like this. So, this anodic part. So, it is going through active zone and then passivity is achieved and then transpassive starts. So, this is transpassive, this zone is passive, and then this zone is, if I try to look at the equilibrium potential for the metal in that solution, equilibrium metal which is dissolving in the anodic part. So, this is metal minus Ne equal to Mn plus. This particular current density corresponds to Ip, which is the lowest current in that particular anodic part. Of course, let us not look at if I try to see the interaction with the cathodic reaction, then this can be sometimes the lowest current density. For example, if a cathodic current then cathodic part interacts here, then this is the cathodic part which is corresponding to IC. So, then this becomes I core. Okay. Now, if this reaction interacts here, so then definitely this is my IC, this is E equilibrium for cathodic reaction, and this is cathodic reaction 1 prime for one type of cathodic reaction, and this is E equilibrium for cathodic reaction, let us say double prime. Fine. So, in one case the potential equilibrium potential for the cathodic reaction is very high in that potential axis. Now, we could see that if we compare these two situations as per mixed potential theory, we have a very high corrosion rate which is located at this location. Fine. So, their corrosion rate would be very high, but somehow if we have some other oxidation, some other reduction process or cathodic polarization line that interacts the anodic polarization line in the passive zone, then of course this becomes my I core, which is equal to IP or the passive current density, which is much lower than the I core what we have observed in case of situation where cathodic reaction polarization line and anodic reaction polarization line they interacts at in the active zone, but here it is interacting in the passive zone. So, we want this thing to happen in case of passive material, active passive material, because once we achieve passivity, it can maintain very low corrosion rate. At the same time, if we somehow choose a solution, if somehow that material shows a wide range of passivity in a particular electrolyte where this material is going to be used, then definitely that passivity will be maintained for a long time, as well as over the wide range of concentration it can maintain passivity. Why? Rather how? So if we try to say this, if we increase the concentration, let's say this is my concentration, initial concentration. If we increase the concentration, I know that if I try to look at the critical concentration, which will be crossing the I critical. If we go back to our lecture 27, you will get to know the importance of this I critical. So, this is just bypassing the I critical point, which is the maximum point in the while the metal achieves while the metal goes or changes from active zone to the passive zone. So, once it crosses, then this particular concentration of that particular corrosive would allow the metal to get into the passive zone. Of course, it has to cross that I critical. It should not touch it, rather it should bypass it. Now, from this concentration, as we increase the concentration, just like increasing the oxidant concentration, the equilibrium potential goes up, and up till this it can actually maintain passivity. But if we see that in that particular environment, my passive zone length is very high. Let us say this is my passive zone length instead of breaking here. Okay. So, if this is the passive zone, which is a wide range of passive zone, okay. So, then I could see that this will be my limiting concentration of the corrosive, where it can, if we increase the concentration little bit, then it will reach to the transpassive zone. So, we can see the from this concentration to this concentration level over a wide range I can maintain spontaneous passivity. That material will go to the spontaneous passivity, and then passivity will be maintained. So, that is what, if we see that between this particular concentration zone, I always maintain the corrosion rate at a fixed value, which is IP. So, that is what it is flat. This particular flat zone is observed, this particular zone is observed, and that happens in case of nickel, two such examples, nickel in NaOH or 18-8 chromium and HNO3. So, there over a wide range of concentration, the material can remain in the passive zone. So, that is what you have a constant current density equal to I passive, and the corrosion rate also remains almost constant. Now, if we in some cases it can follow both 1 and 2, okay, and this happens when the material shows low corrosion rate because of some surface film formation at a lower concentration of the corrosive, but at a higher concentration of corrosive, that film can be soluble, and then once that high concentration corrosive dissolves that passive layer, or not passive layer, is a kind of protective layer here, immediately we can get to see a kind of exponential rise in corrosion rate. That happens, one such example is lead in H2SO4. So, at low concentration, of H2SO4, we can have PbSO4 film, okay, or sometimes it can also form PbO film. But once concentration of H2SO4 goes up at some critical value, this particular phase dissolves. So, that means the bare metal surface is exposed and the material corrosion rate further increases, and sometimes it becomes exponential rise. So, that particular pattern is observed in case of lead pipe, let us say consider lead pipe carrying H2SO4, At a low concentration, it can maintain low corrosion rate, but at a high concentration, definitely lead becomes highly soluble. Okay, corrosion rate further increases. So that's what these two patterns can be observed in case of lead, starting from low concentration of H2SO4 to high concentration of H2SO4. Now there could be one more pattern that can be possible. So initially it's actually gradually increases corrosion rate as the concentration of the corrosive increases, and then suddenly it drops, and then it maintains a constant value. Okay. So this kind of pattern can be observed. Okay. So this let us say this is pattern A, and let us say this is pattern B. In pattern A, we have two segments. One segment we have seen nickel in NaOH or 18-8 in 18-8 stainless steel in HNO3, and pattern A with the segment of 1 and 2, PB or the lead in H2SO4 can follow that. But pattern B is followed if the example, let us say, so these two cases are pattern A. So as we increase the concentration of the corrosive, we have increase in corrosion rate, and then gradually the corrosion rate decreases and then reaches to the plateau. So these happens in case of mainly acid solution. Let us say one such example is 18-8 stainless steel in H2SO4, or another example is Fe in H2SO4. So what happens as concentration increases, H plus ion concentration also increases. So as H plus ion concentration increases, so that means equilibrium potential for hydrogen also increases, because hydrogen ion concentration is increasing. And hence I would see, because hydrogen ion is basically an oxidant and we are increasing the oxidant concentration, corrosion rate increases. But once the concentration reaches certain limit, limiting concentration, the ionization of acid decreases. So once ionization of the acid decreases because of the increase in concentration, hydrogen ion generation also decreases. So that means as hydrogen ion generation decreases and with increase in further concentration, the ionization becomes very limited. So that's why at times, for example, iron, plain carbon steel, if we hold a concentrated H2SO4, we get to see a very low corrosion rate of iron, because of the very situation that concentrated H2SO4 doesn't ionize much, and of course it is at ambient temperature. It's not at a high temperature, it's a room temperature or low temperature. So that case, because we don't have hydrogen ion, which is basically the source for reduction process to happen, and here we should not have dissolved oxygen, fine. So only hydrogen ion reduction is the cathodic reaction. So if we don't have much of a hydrogen ion concentration, definitely the rate of dissolution of iron would also go down. So it will be protected. So this is the case where we can see the pattern B gradually increases because of the ionization of the acid. At certain limit of the concentration, ionization start decreasing, and at a very high concentration, ionization becomes very limited. So then we don't have the active species for reduction process, and the corrosion rate of that metal decreases. Now as you see that the behavior of the metal in a particular electrolyte could be different as we increase the concentration. and here we are not talking about the oxidants. Now, those behaviors should be known beforehand, and that's what experimentation in corrosion protection is very much needed. Now, here you could see that certain metal like 18-8 stainless steel or nickel in NaOH or 18-8 stainless steel in HNO3 at room temperature, it can maintain very low corrosion rate over a wide range of concentration of those corrosives. But in case of lead, interestingly, though it gives you a very good protection at a low concentration of H2SO4, but once the concentration goes up and reaches a critical value, and beyond that, increase in corrosion can dissolve the corrosion product or the product that is forming on top of it, and that gives you the protection, which is lead sulfate or lead oxide, and that can be dissolved at a higher concentration of H2SO4. So then it will expose the surface and it will dissolve quickly. So, what condition will lead to a better corrosion protection, or in other way low corrosion rate or maintain low corrosion rate? We should do a lot of experimentation in the lab scale as well as in the pilot scale, so that we have a better idea, and then we go for change of environment accordingly. So, now if I talk about temperature, effect. Interestingly, almost all the metals, if we increase temperature, the corrosion rate increases exponentially. Now, why? Because all the corrosion is involving electrochemical reactions, and electrochemical reaction, any chemical reactions with increase in temperature, the rate generally increases. So, that is what the corrosion rate is also increases. So, that is what maintaining low temperature is better for better protection of metals and alloys for better corrosion protection. So, what I am saying that lower temperature would give you a better corrosion protection for metals and alloys. Now, it does not mean that at a lower temperature, though it gives you a better protection from corrosion point of view, but it can lead to some other aspects like DVTT, or a ductile brittle transition can happen at a low temperature, and then the material can be very brittle. So, that instance needs to be also considered. We are only talking about corrosion point of view. So, hence decreasing temperature would lead to a better protection or low corrosion rate. So, if I try to look at the graph, let us say temperature increases and corrosion rate, so it would also increase, like it would increase at a very high rate exponentially. Now, in some cases, with increase in temperature there could be a limited effect, but once the temperature goes up beyond certain limit, the corrosion rate can shoot up. Okay. So, it can be like this. So, let us say it maintains a low corrosion rate up to certain temperature range, and then suddenly it shoots up. Okay. So, this particular behavior can also be observed. Okay. So, that means we have two patterns, one is pattern A and one is pattern B. So, pattern A, let us say we can have examples of pattern A. Mainly in case of active metals, this pattern A is very much observed, like nickel in HCl or iron in HF. Okay. There could be a rapid corrosion in those solutions if we increase temperature. Now, pattern B can be observed in case of active passive metal. Let us say 18-8 in HNO3. So, this is interesting. This is also can be explained with reference to mixed potential theory. What happens, this HNO3 can have several reduction potential, standard reduction potential. So, depending on the temperature, its oxidizing ability increases. So, that means what do I mean by oxidizing ability? Increases with temperature increment. Now, let us say metal 1 and metal 2 at let us say ambient temperature, temperature 1, I could have E naught value and here also I could have one E naught value. So, these two values are there at ambient temperature or temperature 1. Now, there could be possibility that this is little, let us say if I consider reduction potential. Fine. So, now if E naught M1 n plus m is greater than E naught M2 n plus m. So, here n plus is nothing but I am talking about two reduction reaction. One is n plus n e equal to m1, m2 n plus n e equal to m2. So, both the cases their oxidation numbers are same. Now, if such situation arises at a particular temperature, we can say that M1 has a higher reduction ability, okay, it as compared to M2. It means that M1 ion N plus ion if it is present and M2 N plus ion if it is also present along with M1 N plus, then M1 N plus has higher ability to get reduced and then deposit on the metal surface. Fine. Now, when we talk about this, let us say if we consider N1 N plus M2 equal to M1 plus M2 N plus. So, this would be reaction then, because M1 N plus has got M1 has higher reduction potential compared to M2. So, it goes to this. So, reduction, and this one goes to this is oxidation or anodic process, because it is releasing N electron which are taken by M1 N plus. Now, we can say that this is oxidant and this is a reductant. Now, we could see that when we have this reaction, now we see that M1 has higher reduction ability compared to M2, as well as we have written the equation where M1 N plus is acting like oxidant and M2 is acting like a reductant, and that is what we have redox reaction, reduction as well as oxidation. Now, when we have such situation, we can also say that this one is actually oxidizing M2, but M1 N plus is getting reduced. So, M2 is reducing M1 plus. So, we can say M1 N plus oxidizes M2 and M2 reduces M1 N plus. And since M1 N plus has got a higher reduction ability, so that means it should have higher M1 N plus has a higher oxidizing ability. Oxidizing ability means it can oxidize other metal with a lower reduction potential. So, here oxidizing ability means that particular acid, this is a very strong oxidant, and all the oxidants have reduction oxidizing ability of other metal. Okay. So, that is what exactly happens here. So, what happens as per mixed potential theory for active passive metal, I can have a plot like this. So, this is my active metal. So, now as per the previous understanding, we are not writing all those details. So, this is the active passive metal anodic part or anodic polarization part, and we see a passive zone, which is this one, the passive zone, this one is basically the active zone. Passive, and then this is transpassive. Now, in this case, initially the material is in passive zone. So, it maintains passivity, or let us say here it maintains passivity. Now, interesting is this is the cathodic part. Corresponding to IC, or the cathodic current density. Now, the corrosion rate would be here, which is I core equal to IP, since this is IP as per mixed potential theory. Now, this particular point lies very close to this transpassive zone, this particular point. Now, if we increase temperature, what happens? The oxidizing power increases. As we have seen that a higher reduction potential means higher oxidizing power. So, oxidizing power increases means its reduction potential also increases. So, the reduction potential goes up. Okay. Now, since it is close to, and as we go up, it will have its own corresponding polarization plot. And we could see that it is cutting at different location, and it is quickly getting into the transpassive zone. After maintaining this passive portion, then it goes to transpassive zone. Definitely once it goes to transpassive zone, the corrosion rate again increases. So, now this is the behavior what we could see here. Okay. What we could see here. So, now here what happens, initially up till this it maintains passive zone, and as the reduction oxidizing ability increases, the reduction potential goes up, reduction potential is going up, and corresponding cathodic polarization line is cutting the active passive anodic part initially in the passive zone and then goes into active zone, which is nothing but the transpassive zone. So, that is what the corrosion rate again increases like this. So, this is a typical of 18-8 stainless steel in HNO3. So, this is the effect of increasing oxidizing ability of the corrosive with temperature or with increase in temperature. So, this happens there. So, and that means we could see two aspects. One is ever increasing corrosion rate with temperature, and this happens in case of active metal. since the reaction rate also increases with temperature. The second case, there could be sudden increase in corrosion rate with temperature increase, definitely both the cases, because of increase in oxidizing ability. So, there could be third instance where we can get decrease in corrosion rate with increase in temperature. So, that instance is observed if we consider iron in seawater or fresh water. So, with increase in temperature, if dissolved oxygen is removed actually. So, in temperature increases, dissolved oxygen concentration decreases, and we know that oxygen is basically the reduction oxidant which actually gets reduced, and then that is the reduction process. It can be O2 plus 2H2O plus 4E equal to 4OH minus. So, if this concentration decreases, so the reaction would not go at a higher rate, definitely the corrosion rate also would decrease. So, it is basically the de-aeration effect of the medium or the electrolyte. So, there could be possibility of decrease in corrosion rate because you are removing the active oxidant from the medium or the electrolyte. So, this is about effect of temperature on the corrosion rate. So, we can sense that there could be possibility of almost all cases the possibility of having low corrosion or a better corrosion protection at a lower temperature. But in some instances, even with increase in temperature, there could be possibility of maintenance of very low temperature, that but once the temperature crosses certain limit, it actually gets to a very active dissolution, and that happens in case of active passive metals, as we have seen in the case of 18H stainless steel in HNO3. But there could be possibility of also decrease in corrosion rate because of removal of corrosive again. Here the removal of corrosive happens because of increase in temperature. So, we will talk about one more important aspect, which is the influence of velocity of that fluid or the electrolyte on the metal corrosion, and we can see whether there could be a possibility of betterment in corrosion protection. Till then, thank you.